Hello, everyone. Good morning.
Good morning.
Good morning.
Morning. I hope you have had a great weekend. Okay. So I think today we are going to continue our lecture in application layer, right? I think this week we can finish this chapter. Okay. There are only about three things we need to mention before end this section or this chapter. Okay, I think you can see my screen right now, right? Still remember what we mentioned last week? So I think we talk about, hold on a second. I think we talk about DNS, right? The general idea of the DNS is to, instead of using IP address, you just use a domain name, right? But it's very hard because it's very hard for you to remember the IP address file. But the problem is that how you can maintain so many or manage so many IP addresses across the world, right? And generally speaking, this hierarchy is very important because this is a distributed hierarchical database to manage the domain name system. Okay, so it's from the root DNS server to the top level domain and the final authoritative layer. Okay, and I believe you should know that after you watching the video I played to you, I played the video to you, right? So this is what we mentioned last week. And an interesting thing that actually I used something during the weekend, especially with the DNS thing. So a quick story I can share with you. So I established a web, just a web in GitHub. Okay, I use what GitHub provide to me. I think it's I just write the YML code and I can generate the automatically generates the GitHub web page. Okay, and I think the problem or the only concern I'm using the GitHub web page is because of the domain name. Okay, so the domain name is a kind of not very professional. I think if you notice, for example, something.github.io, right? So if you want to maintain a organization web page or maybe personal web page is fine, but you can also use another domain, right? So how I deal with this is I purchase a domain somewhere else from WIX Wix or from the other domain provider, right? And after that, the thing I need to set up is if I input, for example, how should I say? Okay, so for example, I want to establish a web page like www.drtao.org or .com, right? But in the GitHub, I cannot have that domain name. So I purchase a domain name like www.drtao.org, right? And after that, I need to use create CNAME. So it's what we mentioned, right? That's a record. We need to direct once I input the www.drtao.org, it will automatically direct the people to the GitHub link, right? And I need to set up something here. Similar idea, very similar idea here. I need to input the DNS record in the DNS server. And every time people input that address or org address, then it will automatically direct people to the GitHub link. Okay, so I think maybe I can quickly show you what I have set up. Hold on one second, that maybe better to explain this. That's interesting. I want to share with you because I think it's a very um, lucky or maybe a coincidence that I was setting up something really related to what we talk about in the class. Okay, so I think this is what I want to create. um, you can see my GitHub page, right? This is what I want to set up. We establish a software, we have a project, and we want to release that project as an official website, right? And the problem is that this is a thing I set up in GitHub, okay? So if, if I don't purchase a domain, the only thing I can do is just input the scompressor.github.io, right? So this is a domain name, okay? So if I don't do anything, if I don't purchase anything, that would be our domain, okay? But the thing is that I want to use something like scompressor.org, right? I want to use that domain, right? Domain name, because that looks more professional. So the thing I needed to do is that first I needed to change here. This is a custom domain. The only thing, actually, if you input something here, the GitHub will automatically add a CNAME record here. Okay, it's just a create a CNAME in GitHub server. Okay, but things that I also need to let my original domain server uh, here is a scompressor.org, right? I purchased this domain somewhere. So that domain name server, I also need to let that domain name server know that how or where it should direct the people's request to, right, to GitHub, right? So for example, I purchased this in Wix, so I need to set up in Wix that domain name direct to the GitHub IP addresses. And then if it's a direct to the GitHub, GitHub would be the final layer, right? The authoritative layer would know the IP address of my web page established in the GitHub. Okay, this is something very close to what we talked about in the last lecture, right? We have to put a record. Let me go back to the slides. Still remember here, we need to put a DNS record, right? Some DNS record is just the host name plus IP address. But for my case, right, I need to use this CNAME. This is the name is aliased for some other web page, right? So that means I need to set up www.scompressor.org. Actually, it is pointed to the GitHub web page. It's the scompressor.github.io. That's the point, okay? But I need to set up something in the domain name server and configure something to make it happen. So this is just happened during the weekend. I feel very interesting because we just talked about this idea in the lecture, right? So I believe some of you may also have this appearance just to configure your domain name in GitHub to establish a website, right? Something like this. Okay, this is just a quick story I want to share with you because I think it's interesting. So from this week, let's go to the final 3 applications in network. Okay, P2P application, video streaming, and the socket programming. Okay, so first, what is P2P? So I think I remember the different paradigm, right? Still remember client and the server and peer-to-peer, right? That's two major, let's say the architecture or maybe the model or the diagram, right? Whatever you want to say, but that's a two general model. One is client and the server. I think previously we talked about HTTP, FTP, email, and DNS server, all the things about a client and the server, right? Server and client. But now today we change to another model. It's our architecture is a peer-to-peer. So it's not difficult to understand from the word, right? Just send some information or switch some information between two sides, and two sides are equally important, right? No one is a master, no one is the client, no one is the server, right? Both sides could serve as a server, could serve as a client. okay? So the reason to have this architecture because it's no always on server, right? Sometimes you need to close your server, right? Maintain your server. Um, it's no guarantee for always on server, right? And the arbitrary end system directly communicate, right? So you can ask different end system to direct communicate with each other. So we will see a calculation or modeling later. This method can significantly improve the or reduce the communication overhead. For example, if some of you, I think, mentioned that the BitTorrent, right? So if you use that to download some file, we will explain that why it's much faster than direct download from server. It's not always much faster, but generally speaking, more users are using that, and then it would be much faster. Okay, so we will explain why this is happening, or why P2P can make this happen. Okay. So peers request service from other peers, provide service in return to other peers. So this is something can guarantee the self-scalability. So we will give you a formula, as I mentioned, to help you understand why this is a self-scalable. Self-scalable means that you don't need to increase the capability in the server side, right? So if you add more end system or peers into the network, then the scalability increases automatically, right? It's self-scalable, right? Okay, so new peers bring new service capacity and new service demands, okay? So peers are intermittently connected and change IP address, right? Um, this is something we mentioned before, I guess. It has a complicated system to manage the IP address or a different end system in the network. So there is some scheme there. So the example of the P2P architecture is the P2P file sharing, BitTorrent, right? And the streaming, I think the CanCan, right? I will show you a figure there. So maybe some of you um, do not use that before. And there's VoIP, Skype is also point to point, okay? But I think the BitTorrent is a very famous P2P file sharing. And if some of you have the experience that a lot of people are trying to download a movie or some big file, BitTorrent could provide you a better service or capability to download the large file, okay? So let's first think about why client server model. What is a client server model disadvantage, pros and cons, right? So if we think about from the modeling perspective, right, we have the different upload and download speed, and we have different bandwidth, right? What is a general, what is rough or estimate the time to download or share the file if we use the two different models, right? Client server model versus P2P model. So for example, here, let's use an example. For example, if we want to distribute a file of size F from one server to N peers, it's just like a simple model, right? We have a server here and right? We have a server here, and we have n peers from 1 to until n, right? So we have n peers. And what is the time if we want to distribute this model from one server to n peers? That's our question, right? We want to calculate something here. Okay, so okay, so from the server transmission, it must sequentially send or upload n file copies, right? Because server, our assumption is that the server is in full execution, right? If you want to download or upload n copies of the files, you have to do one by one, right? So the time to send one copy is F divided by US, right? So use I think here use the speed from the server to the network, right? This is speed for the server US, and the D means the download speed, right? So here for server side, the time to send one copy is just the file size divided by US. And if we have the N copies, the time would be N times F divided by US, right? This is not difficult to understand. And for client side, so each client must download the file copy. Okay, so we have the different download speed for different peers or for different clients. Sorry, I should use a client, right? Here, no peers concept. So let's say client, if we have N clients and each client has a download speed of DI, right? So the speed would be, the time would be F divided by DI. And we want to know the minimum client. I think it should be max, right? So dmin means client download rate, mean client download rate. So if F divided by dmin, that means the max client download time. So we should care about the maximum time, right? Minimum time is not the point we want to concern about. We want to know which one is the latest one to get the file, right? The overall time, right? So I think dmin means that the mean client download rate. So max client download time would be F divided by dmin, okay? So consider these two parts because these two parts are happening together, right? During the meantime, you download something, the server could upload the data to the network to other servers. So the time to distribute the F to N clients using client server approach is larger or no smaller than max NF divided by US, and between these two numbers, right? And F divided by D mean. Okay, so any question about this model? I think this is very simple, straightforward calculation, right? N times F, because we have N copy of the file, need to be sent from the server side. So NF, right, the total file size divided by US is the upload the speed from server to the network, right? And the F divided by D mean is the maximum download time for the N clients. Okay, so this is a client server model. I think there is a question. Let me try to see. This is a good question. I think I mentioned that the mean is the mean time, is the mean download rate across all clients. So let's say if the fifth client has a lowest download rate, then the maximum time for all the clients to download the file is F divided by D5, right? So this means that across all the client side, right? Not only the mean speed for this client, okay, for N client, which one is the minimum? Is that clear, Ace?
So the majority of tasks that are normally designated for the server are being achieved by the clients in this model.
Yes, you are right. Yes, I think you are right. And yes, that's correct. You can see here. So the time, let's say it depends on the US and the D mean, right? So you can think about if N is very large. So I think your point is kind of right. Mostly we say that the time could be limited by the download rate, but the problem is that sometimes this N is also very large, right? If you think about millions of the clients in the network, okay, the server has a very huge burden to upload all the copies of the files to the network, right? It will be sequentially happening and also increase linearly with the N, okay? So So my point is depends. If n is not very large, then the bottleneck would be the slowest client in the network, right? For example, if you have a very powerful server, but you only provide the service or the download the file or upload the file to the other maybe 5 or 10 a few clients, right? Then the bottleneck will not be here, okay? The bottleneck would be here. So depends on maybe the slowest client you have, maybe a cell phone, right? Maybe something very slow, right? It downloads the network, downloads the file from network. Um, but if n is very large, then the bottleneck would be the server side. You can think about one people provide service to millions of the people, thousands of people, then that people provide the service would be very quite busy, right? And it has a huge burden. And if we are using the P2P model, so here is a P2P model, okay? P2P architecture. So the model is that we ask each client to download the, let's say, so first from the server side, you must upload at least one copy, okay? You share the file to the copy, you share one copy of the file to the network, okay? And after you share that copy, and the different server could get the copy, part of the copy, and the different server would exchange the part of the file with each other. Okay, so here the main difference that the server only provides, for example, one copy. So the time to send one copy is F divided by US. Okay, and this is also the same. So the mean client download time, I think it should be same typo, right? So maximum client download time, because mean is the mean speed. So F divided by mean. Okay, this is a two. The second term is the same, right? The first term is we just upload the one copy, and what is something you need to pay attention here is we need to have aggregate master download NF bits, and the maximum upload rate is this formula. So how we think about this third term? So this third term means that you have to have n copies of the data or files exchanged between the peers or between the clients, right? But the maximum upload rate you can have here is a US plus all the other clients working together. So it's like you aggregate all the upload rate together, because you know that at least you need to upload n files. That n files not maybe from the server side at one time, but could be from the different other peers. But you can calculate the overall data transmitted in the network, right? Because every peers or every servers needs to have a one copy. So the total size should be n times f bits or byte, whatever, depends on the beginning of the f, right? Maybe beginning of the f is f bits. So we have the n times f. So the total size you need to download is n times f. That means you also need to upload such large of the data, right? And the aggregated upload rate is US plus all the UI together. So why we care about U, not D? So we can also say that we use NF divided by D, right? Because the upload data size should be exactly the same as the download size, right? So why we use NF divided by US plus all the UI, the sum of UI here, not D? Anyone know that? So the multiple seeders, I mean, is the point we want to aggregate all the U together. So my question is that why we use the US here? Because we have the U and the D, right? U is the upload speed. So we use the F times N divided by US is the server side upload rate plus all the aggregated upload speed from the N server here. My point is why we use a U instead of put the formula D here, DS plus, or not US plus maybe sigma or sum of the DI here. I think the point here is that I think we mentioned that before, because the current cable or telephone telecommunication company provides a service to you is not symmetric, it's asymmetric. Okay, that means the download speed is usually faster than the upload speed. Okay, so here we have the upload rate and download rate. If you can do a simple test, or I mean, if you can quickly search online web to benchmark your network service. For example, you have the 25 or 30 or 80 or even 100 megabits per second network, right? How you can measure that network, or how you can guarantee your provider provides the good service to you. You can do an online benchmark, right? There is a web page to help you understand what's your current network status. And then you should notice that the upload speed is kind of slower than download speed. Okay, so here we only care about the slower one, right? So upload is slower than the download. So we use NF divided by the aggregated rate of aggregated upload rate here. Okay. Want the maximum value of those always be the last one? You mean the maximum value of this three term would be the last one? Yes, you're right. So, I mean, considering a large N, right? Our assumption is we have a large N, right? So as I just told to Joseph, so if the N is not very large, then the bottleneck would not be the last term. But in general, we have a large N, then the bottleneck would be the last term, okay? And you can see here, so this, oh, sorry. So this large term would increase linearly in N, but the good thing is that it's NF divided by something. This thing also increases when you increase the number of the peers or servers in the network. So N increase, this term also increase. Right? Sorry, I should use the laser. Okay, so if N increase means that the number of the clients increase, right? Increases. But these terms also increase, right? Because you put more aggregated or higher aggregated upload rate. So both side, numerator and denominator are both increasing, right? So that means this term would be relatively stable or not increasing very fast or exponentially or something, or linearly, right? Or not exponentially, but not linearly, right? Non-linearly, okay? So I think there is a figure here. To give you the idea, if you use client and the server, the minimum distribution time, if we increase N, it's just a linear. So if you look at this formula, right? So if N increase a lot, then the first term would be dominant, and then the time would be increased linearly, okay? Like this black dot line, okay? But if you use a P2P model, right, as we mentioned, it's still increasing, but it's much slower than linear, okay? So that means that we can self-maintain the scalability. We can maintain the self-scalability, right? Let me see if there's any question. Gotcha. Both the numerator and numerator. Yes, yes, that's right. Right. So it's very kind of interesting, right? So use a P2P. I think if you don't think about the model or your number or your formula, you just jump out of the numbers. You can think about you have n clients, right? The server maybe just serve as another client or powerful client. You have a n+1 client there, and if the data is maybe shared across different servers, um, client just send maybe you have the piece one, he has a piece two, and she has piece three, right? We three people can switch between us, right? We don't need a central server to send the data one by one, right? That's a general idea why P2P is sometimes faster, especially when N is very large. Okay, N is not very large, your central server is fine, right? They have the capability to provide a good download, upload service, right? But if the N is very large, then P2P would have a better or more obviously, I mean, faster speed, right? Because it's self scalable. Okay, so this figure give you the idea. You can think about like a simulation, right? Or just based on the model to calculate the client server, to calculate the minimum distribution time with the client server or P2P architecture. Okay, so this is um, uh, the basic idea. We will give you an example. What is a P2P application, right? Like a BitTorrent, right? But before that, from the high level, you should understand why P2P is faster than client server model. Okay. So let's talk about BitTorrent, right? This is something maybe some of you use that before or still use that, right? So it's the idea to cut or divide the files into the different chunks. For example, in BitTorrent, it's about 256 KB per chunk. Okay, it cuts the file, divide the file into the different pieces, and the peers in the torrent that network, right, send and receive file chunks. And the idea just we mentioned is not the central server to send each chunk to send all the chunks to one client one by one, right? It's just to send the piece to the whole BitTorrent network, and they can exchange the chunk of the data by themselves, right? So we have the tracker, right? So it's not like it's kind of the server, but in this model we call it tracker. Oh, okay. So tracker is just tracks the peers participating in torrent, because someone can anytime join, someone can anytime quit, right? If you finish downloading, definitely you want to quit and close the BitTorrent software. You may not provide the data to other people, right? So we have to have the tracker to track which peers or who are participating in the torrent, right? And the torrent is a group of peers exchanging the chunks of the data to fill up other people's work, right? Or data exchange. Yeah, I think the multiple trackers would make the big torrent network, more efficient, right? But at least we need to have one. And from functionality perspective, one is okay, but one is not efficient because sometimes a lot of peers join and quit, right? So multiple tracker and may have a better scalability or performance here. Okay, so let's say this is some, hold on a second, I think chat block my text. Sorry, I should reshare. Sorry, today I didn't use I don't use a second screen, so kind of everything centralized in my screen. My second screen is not kind of working. I need to fix that. But anyway, okay. So this is a quick example. For example, Alice arrives and it obtains a list of peers from tracker, right? If you have more or multiple trackers, definitely you can get this list faster, right? And then it begins to exchange the file chunks with peers in the torrent, okay? So let's see, here is more details, So peer joining torrent, it has no chunks at the beginning, right? But will accumulate them over time from other peers. At the beginning, you have nothing, right? You just wait for some other people to give you something. After that, then you can have something to share with the people, right? That's the idea. But at the beginning, you just obtain things, right? More than the thing you sent, right? And you need to register with the tracker to get a list of peers, and you self also register in the peers, right? And connect to subset of peers, neighbors, right? The neighbors also have some mechanism here. You don't want to connect to some peers very far away from you, right? You don't want to connect to some peers similar to you just arriving, right? You want to connect to some peers or some neighbors have a kind of bunch of data can share with you and also make close to you and provide a good peer-to-peer data exchange, okay? Okay, so next is while downloading, people upload chunks to other peers, as I mentioned, right? During the meantime, you downloading the files, you can upload the chunks of the data to other peers, and the peer may change peers with whom it exchanges chunks, right? Because it cannot always guarantee that peer will always be there, right? For example, if someone finished downloading, they can just quit, and you are still exchanging the data with it, with that peer, then your connection will be disconnected, right? Will be disappeared. So you have to change, maybe. So I think there is a scheme to examine if the 256 KB has been finished or not, right? If during maybe if you haven't finished that trunk, you need to find another peers to resend that trunk to you again, right? Because the people just not just quit, right? You have to find someone else. Okay, so the churn peers may come and go, as I mentioned, right? Sometimes join, sometimes go. You cannot guarantee you always exchange the data with some certain peers, right? So once peer has entire file, it may selfishly leave, or you just serve as a peers to send the data, share the chunks of the data with other people, right? So if you want to be selfish, you just finish downloading and then quit Bit, because if you open the BitTorrent software there, you will always provide as a server side because you have already finished downloading, right? The only thing you can do is to share your data with other people. So if I'm selfish, I don't want to the BitTorrent to dominate my network, right? To consume my bandwidth, then I just quit, right? But sometimes if you forget that, but sometimes if you just maybe during the time you are working, you just put software there, you can play as a server side, right? Okay, so next is requesting sending files about a BitTorrent. So it's a requesting chunks at any given time. Different peers have the different subsets of the file chunks, right? This is a definite. And periodically, the Alice asks each peers for a list of the chunks that they have, right? You have to know who have which kind of the chunks, right? You have to know the list. And the Alice requests the missing chunks from peers, rarest first. Okay, so you have to have some scheduling, right? As I mentioned, you need to, for example, here you request missing chunks from peers rarest first, right? It can provide better transmission. And also for sending chunks, okay? So Alice send chunks to those 4 peers currently sending her chunks at the highest speed or highest rate. Other peers are tracked by Alice, do not receive chunks from her. Reevaluate top 4 every 10 seconds. So I think the idea here is that if someone share the data with you at a very high speed, then you should return something to them, right? Because someone share good thing with you, you should share some good thing with them, right? So that's why Alice sends chunks to those 4 peers currently sending her chunks at the highest rate. The idea is that reward, right? Some people give you something, you reward some people other thing. That's the idea, right? I think this is fair, right? If someone's sending your data very slow, then you should share that chunks of data to other people at a higher speed, right? And this is reevaluated every 10 seconds about the top 4 users, right? And every 30 seconds, randomly select another peer, start sending chunks, because you want to expand your data sharing, right? You sometimes if always these 3 people, 4 people sharing their data together, you cannot guarantee the other people, even in the network, even with the slow speed, they still want to get something, right? You still want to share something with other people, but may not be such a high speed, right? So every 30 seconds, you random select another peer to make sure that you can do something for other people, even they are not share the data with you at a very high speed, okay? So newly chosen peer may join the top 4, right? So that's something like you want to have a collaboration with the people. You always find the people read your paper or maybe give you the better suggestion or comments, right? But because you want to extend your circle, right? You don't want to only focus your small community, then you can randomly select some people to send the paper, right? And share your project. And maybe the people are interested in your project and talk to you and they become the person in your community, right? So that's some idea in socialization, right? In your social scenario, same thing, right? Okay, and this is explanation of the BitTorrent and BitTorrent. And okay, so here is some tat, and Alice optimistically unchokes Bob, and Alice becomes one of Bob's top 4 providers, and Bob just rewards that, right? Just notice that you becomes my top 4 providers. I should do something for you as well. The Bob becomes one of Alice's top 4 provider. That's what I mentioned. Higher upload rate, find better trading partners, get file transfer faster, right? So that's why we, not we, but the BitTorrent every 30 seconds randomly pick up someone, right? Some peers in the torrent network, but always doing the good thing for the peers, giving you the high transfer rate. Okay, so that's the idea about P2P application. Okay, so any question before I go into the video streaming? I don't think I have much time to give you the idea about video streaming. Just the last 5 minutes, but let's have a quick start. Okay, but just a quick check if you have any question about the P2P application. We don't focus too much thing like email or HTTP about what is the protocol message look like, but we more talk about from the high level, right? This is also a protocol, right? This is also a protocol, but not just the protocol message format something, right? This is also scheme, how you use a P2P or BitTorrent to exchange the data with other people. This is also a protocol, okay? P2P, let's say this is a P2P protocol, okay, for the BitTorrent. Okay, so if you don't have question, let's quick start with the video streaming so that for the next 2 lecture, we can finish this chapter, okay? So video streaming, I think most of you, or maybe at least for me, when I have some time to have a rest, most of the time I spend is watching the video, right? In Netflix, YouTube, Amazon Prime, all of the providers provide good video or audio contents, right, to the network, to the internet. And you can see that 80% of the residential ISP traffic has been spent in the Netflix, YouTube, Amazon Prime, right? People are always watching shows, right, and watching a lot of interesting videos, right? And the challenge is that how can we make this scalable, right? If a lot of people are watching the video online, right, doing the streaming things online, for example, 1 billion of the users, how can we reach that? How can we make this um, the still this services efficient and scalable, right? So the single mega video server won't work. So that's a similar idea, definitely a similar idea, right? If you only have a one video server, as we mentioned in last um, several slides, the P2P versus the client server, right? Just only one server provides a video to everyone doesn't make sense, right? We need to have some better idea how we can um, provide you a good streaming or video service, right? The challenger is the heterogeneous, right? The heterogeneity. So the different users have different capabilities. Sometimes you use a mobile, sometimes you use laptop, you have different bandwidth, right? Sometimes bandwidth is very rich, right? You can just immediately load the whole video, right, at 1 or 2 seconds, but sometimes the speed is very poor. You have to wait maybe 10 or 20 seconds until you can watch just 5 seconds. That's also possible, right? How we can deal with such a situation, okay? So the solution is a distributed application level in structure. Oh, okay. So here is the logo for 迅雷看看, right? This is a very I mean, at least a very famous software in China, I know. So people are using, this is a P2P streaming, a video streaming software, right? It's not quite like a Hulu or Netflix, YouTube. It's like a more like a P2P service. And I think it's famous in China. Okay, so at least I know some of my friends are using this. Okay, and definitely YouTube, Netflix, Hulu are very famous in US or in the world, right? And the multimedia video. So the video is a sequence of images placed at a constant rate. So we can see we have some video like 24 images per second, right? And for the image, it's like an array of pixels, each pixel presented by bits, right? And this is something related to my research, right? But not exactly the same. So we also do some encoding, but we are doing something for the other kind of data set. But in video or audio, the encoding is very popular and famous because you want to use the redundant information between the image, video, audio to reduce the size or data size or file size, right? To improve the streaming performance or to improve your network bandwidth, right? Because, for example, I have a record, or I have a recording of my lecture today, right? It's about 200 and 100 megabytes. I need to upload the video to our learning Blackboard system, right? If the file is not encoded very well, maybe I guess it could be more than 500 megabytes. It could be 1 gigabytes, right, with a very high resolution. Then the problem that how you can watch 1 gigabyte of the video for 40 minutes, right, using poor network, right? So encoding or to make sure the video or images have a less size or smaller size is very important. So some kind of the encoding techniques can be used here. For example, for image, right, you can see the first image showing above, right? So it's a lot of spatial information that can be removed directly. in the compressed format or in the encoding, right? You can see the background just purple, right? A blue or something. You almost all the pictures here in background are the same, right? So we can remove that. Okay, we can use one value or less values to store that, right? And also, if you are playing a video, each frame has some similarity, right? You don't need to save all the frames one by one. You can just save the difference between the different frames, right? And the value could be sometimes close to zero. You don't need to save anything, right? Zero is nothing, right? You don't need to save something. So yes, I think this is very close to what I'm doing research in the scientific data compression, right? I think I just show you the compressor web page I established during the weekend. That's one of our projects, right? Similarly, we use some kind of encoding technique to reduce the data size of the scientific data, right? Like biology or cosmology or some chemistry data set, right? It's similar. But the idea is that in the network, we have a lot of data can be lost, as I mentioned, right? And you have the demand to do a very high performance streaming service. Okay, so I think that I over time. Okay, just 1 minute over time. Okay, any questions? So we can continue next lecture about the streaming, our content network. Okay, so any question before we end up today? Oh, okay. So for information, I think the TA has already graded your assignment. So if you have any question, just let me know. And I didn't check for everyone, but if you think your score or grade has any problem, just let me know. Okay, I can check it again, and if it has any problem, I can ask TA to regrade. Okay. So I believe I will post the assignment today. Okay, later this afternoon. Okay, so if no questions, thank you everyone to attend. We'll see you on Wednesday. Okay, bye-bye everyone. Thank you.